All right, guys, we're just continuing on here with what we left off with for finding more examples or finding the intervals of convergence and testing the endpoints. So last time they were all geometric. This time we'll do some that are ratio, use the ratio test. So we want to find the radius of convergence and the interval of convergence for each one. So the first one here is the sum of n factorial times x to the n. So we can't just do geometric here because we've got... Where's my pen? There we go. There's my pen. We can't just do geometric here because we have these extra n's outside of the exponent. Like if all the n's were inside, then we could try, well, no, then we'd still have issues. But if we just had all numbers inside raised to the n, then we could do that. But since we don't, we need to do this as a geometric, or sorry, as a ratio. Sorry. So we've got n plus 1 in here. So n plus 1 factorial x to the n plus 1 over just the original guy. X factorial, x to the n, n factorial, x to the n. And we need this, again, to be less than 1, less than or equal to 1, I guess. All right, so what we do is, well, we just start canceling out stuff. So all the x's are going to cancel out except for one x on the top. So really, we've got absolute value of x on top. All right, here, n plus 1 over n factorial, that's n plus 1 times n minus 1, and so on. So times n factorial, and those cancel out. So we get n plus 1 times the absolute value of x needs to be less than 1. All right, but don't forget we're taking the limit. So if we divide this over to the other side, we get the absolute value of x has to be less than 1 over n plus 1. All right, now if we take the limit as n goes to 0, less than or equal to, I suppose, we get that this goes to 0. All right, we get infinity on the bottom, 1 over infinity goes to 0. So it looks like our radius here is 0. All right, so that means we're only going to converge in one particular space, and that's where this is centered. So it converges at specifically the set of just 0, or you could say when x equals 0 only. All right, that's the only place it'll converge, because if we plug in 0 here, the first term will be 1, every term after that will be 0, and it will converge. Otherwise, if we have any other number here, this n factorial is going to get bigger than that number and make it diverge. Like it's going to go off to something big. All right, so let's try another one over here. Find the interval of convergence. We've got 3x to the n over n factorial. All right, so again, we don't just have something to the n, we've got this extra n factorial down here. So we've got to try and do a ratio test. So we're doing the limit as n goes to infinity of the absolute value of this guy with n plus 1 plugged in. And that is a 3. And then divided by this guy with n. So we'll just flip and multiply n factorial over 3x to the n in absolute value. So this 3x to the n is going to cancel out completely and leave us with just this 1 on top. This n factorial is going to cancel out completely and just leave us with an n plus 1 down there on the bottom. So we get the absolute value of 3x over n plus 1 is what we're getting here as n goes to infinity. And we need this to be less than or equal to 1. Right? And the reason I'm putting this kind of dotted line here is because really it could be equal to, we don't know. If it equal to works, then we have to plug it back in here to check for sure if equal to works. All right, I guess we could say strictly less than and then remember to check what happens at the endpoints afterwards. So if we multiply this guy up, we get the absolute value of 3x is less than n plus 1. And this is, again, the limit as n goes to infinity. All right, so even if we do divide both sides by 3 to get rid of that 3 there, we still have n plus 1 over here. All right, and as we go to infinity, that gives us infinity. All right, so that means our radius of convergence is infinite. All right, it doesn't matter what x is, and on the bottom here with the factorial is going to get so much bigger, it's going to go to infinity. All right, so then what happens is that converges from negative infinity to infinity, or for all x. All right, so n factorial makes a big difference. If it's on top, it only is going to converge at the 0. If it's on bottom, it's going to converge pretty much everywhere, at least in this case. Unless there's something else on top or on bottom to cancel it out. All right, so find the radius of convergence for this guy. Oh boy, oh boy. Let's see what happens here. So, definitely not geometric, so we're going to have to do the ratio test. The limit as n goes to infinity of this guy with n plus 1. So when we do it, we have absolute value here. The negative 1 is just going to cancel out in here, so I'm just going to leave it out. So we're going to have x to the 2 n plus 1 over 2 n plus 1 factorial times, and then this guy flipped over, because you're really dividing by this whole thing. So this will be 2n plus 1 factorial over 2n plus 1. Oops, sorry, x to the 2n plus 1. There we go. All right, and we want that to be less than 1. So let's see, this is going to be 2n plus 2 plus 1. So that's going to cancel out completely with that one and leave us with x squared on the top. So really we just have, say, x squared, like that. Because the plus 1 and the 2n plus 1 and the 2n all cancel. This guy, this is 2n plus 2 plus 1, so 2n plus 3 factorial. So that's 2n plus 3 times 2n plus 2 times 2n plus 1. Now it matches, so I'll just put the factorial there. Those are going to cancel. So we've got the absolute value of x squared over 2n plus 3 times 2n plus 2, and we want that to be less than 1 as we go to infinity. All right, well, if we move these guys up, what happens is the absolute value of x squared is less than 2n plus 3 times 2n plus 2, which as we go to infinity with n, this guy goes to infinity. So there's our radius here is infinite. All right, so we're going to converge for all x. So it converges from negative infinity to infinity. All right, hopefully we'll get some more entertaining intervals here in a moment. Since right now we've got mostly boring ones. All right, so next one. All sorts of things going on here. Everybody is raised to the n, so we probably could do this one as a geometric if we want, but let's do it as a ratio just to see what happens when we get an actual interval for ratio. So again, the negative 1 is going to cancel, so we can leave it out. X plus 1 to the n plus 1 over 2 to the n plus 1, and we flip and multiply x plus 1 to the n, and we want that less than 1. So this guy cancels out completely. We're left with an x plus 1 on top here. 2 to the n is going to cancel with this guy. We have one extra 2 down on the bottom. So we get x plus 1 in absolute value over the absolute value of 2, which is just 2, is less than 1. The limit as n goes to infinity. There's no n's left, so we just multiply up to 2. Is less than 2. So this is our radius over here, 2. Right? And if we solve this, so we'd say negative 2 is less than x plus 1 is less than 2. We'd subtract 1 everywhere. We get negative 3 is less than x is less than 1. All right, now since we did ratio, we actually have to test both endpoints just to make sure. So if we test x equals 3, sorry, negative 3, then we'll have the sum of negative 1 to the n, negative 3 plus 1 to the n, over 2 to the n. So this is negative 2 to the n. And the negatives here are actually going to cancel each other out, because whenever this guy's negative, this one will also be negative, so this just cancels out completely. We get 2 to the n over 2 to the n, and we end up getting the sum of 1, which diverges. All right, I think just about a similar thing is going to happen, well, slightly different, I guess, is going to happen when we plug in 1. So we'll have negative 1 to the n, 1 plus 1 is 2, so we get 2 to the n on top, 2 to the n on bottom. 2 to the n's cancel out, we get negative 1 to the n. So that's just going to go back and forth between, I guess, 1 and 0, right? We'll add 1, we'll subtract 1. We'll add 1, we'll subtract 1. So it oscillates. It does not converge. It diverges. So our interval of convergence is just this. We don't include either endpoint here, or we can say it's negative 3 to 1, like that. All right, 2 more here. What color haven't I used yet? Green, sure. Find the interval of convergence, x to the n over 2 to the n. So all of them have some sort of x to the n, gosh, except for this one, and there we go. All right, so again, we'll look at the ratio test here. So we'll do the limit as n goes to infinity of x to the n plus 1 over n plus 1 squared times, and this guy flipped over, n squared over x to the n. X to the n cancels, leaves us with 1x here. And these guys, n squared over n plus 1 squared, as we go to infinity, again, we just look at the highest power on top and bottom, and this whole thing here just goes to 1. Right? N squared is the highest power on top, n squared is the highest power on the bottom. The coefficient for each of them are 1, so we get the absolute value of x is less than 1. So that means this is our radius right here. So we're going from -1 is less than x is less than 1. We can plug in both endpoints to see if it converges. So if we plug in -1, we want to see if we can include these endpoints. So we'll have -1 to the n over n squared, which does converge. If you want, you can say it's an alternating series test. All right, it's always going to be decreasing, and the limit goes to 0, so that guy converges. If we plug in 1, so we'll have 1 to the n over n squared, which is really just 1 over n squared, which is a p-series, where p equals 2, so that means that also converges. So both of these converge, so we get that the interval actually goes from -1 to 1, and we include both endpoints. Or we can say equals on both of them like that. All right, and back to red here. So again, this exponent was supposed to be an n, not a 2. Hey. All right, so again, we're going to do the ratio test, limit as n goes to infinity. So this will be x minus 1 to the n plus 1 over n plus 1, again in absolute value, n over x minus 1 to the n. We want this to be less than 1. All of those x's are going to cancel out except for 1 here. And we're going to be left with the absolute value of n minus 1 times n over n plus 1. We're taking the limit as n goes to infinity, and we want this to be less than 1. This n over n plus 1 term, again, is just 1. As we go to infinity, we're just looking at the coefficients, 1 over 1. So we get the absolute value of x minus 1 is less than 1. So that means this right here is our radius of convergence, 1. And if we solve, we say -1 is less than x minus 1 is less than 1. We add 1 everywhere. So we'll get 0 is less than x is less than 2. All right, now we have to check both endpoints. So if we check x equals 0, we're going to get the sum of 0 minus 1. So that'll be -1 to the n over n. And this is an alternating series, which converges. All right, it's always decreasing. The limit goes to 0. If we plug in 2, we'll get 1 to the n, or just 1 over n, which diverges. It's a p-series, or it's the harmonic series, with p equal to 1. So that means we want to include the 0, but exclude the 2. So we can say that right there is our answer, or we can say it's from 0 to 2, including 0, not including 2, like that. All right, so that's 6 more examples, so hopefully that'll get you through how to do the homework. There is still one more video here, so check out the next one.